Good evening, everyone. This will be the start of a new series that I'm working on, which mainly covers the basics of cellular respiration. What I aim to do with this series is that I aim to go through the basics of cellular respiration, and then on a later note, once all that is done, I want to go through and review the literature and analyze the specific individual biochemical reactions that occur within some of the processes of cellular respiration. Most notably, the citric acid cycle as well as glycolysis. So, but what we first have to do is first go through the basics, which leads me to today's purpose of the lessons, which is energy transfers. So the basics of energy transfer as well as the role of ATP in biosynthetic reactions. So let's first start with reviewing equilibrium and the steady state. So equilibrium is the point in a chemical reaction where the rate of the forward reaction is equivalent to the rate of the reverse reaction. So they're both taking place simultaneously at equal rates. No energy is required to maintain this state, and no energy can be extracted to do work. So this means that in a system, all systems tend to be reaching towards equilibrium, and all the reactions are what characterize the process of reaching equilibrium. So for a given reaction of A plus B is converted into C plus D, the equilibrium constant is equivalent to the concentration of the products over the concentration of the reactants, as shown below here, where lowercase letters are also representative of the coefficients, and you can see here that down below that the coefficients actually are represented in powers when we describe the equilibrium constant. So with regards to that, we also want to look at the concept of steady state, where the point in a chemical reaction, steady state refers to the point in a chemical reaction where the amount of products and reactants remains constant. So this means that within a system, we observe that the concentration of both the products and the reactants remains constant. So in closed systems, a steady state equilibrium means that the concentration of the products and reactants remain constant, as described by the terminology of steady state. No work can be done to change the concentrations, hence the reason why the steady state is equivalent to the equilibrium, and only heat can be exchanged between the system and its surroundings. In open or living systems, in essence cells, the steady state is not equivalent to the equilibrium, meaning that reactions will never finish, in essence never reach equilibrium, but they're always working towards reaching equilibrium. And the concentrations of the products and the reactants are maintained, but the energy, and therefore work, and more specifically the potential energy, but energy is required to maintain the concentration, to maintain the relative concentrations of both the products and the reactants. Hence, maintaining a certain point away from equilibrium. So we see here that energy can be expended to push the situation away from equilibrium, making the system unstable and higher in potential energy. Hence, delta G being, or Gibbs free energy, being greater than 0, and allowing the system to try to return to equilibrium means energy can be extracted to do work. Delta G, or the change in Gibbs free energy, is less than 0. No work is applied, and therefore the system is permitted to returning to equilibrium, releasing energy in the process, as shown here. Right? So work is expended in this reaction here. Work here isn't applied, and since the system is allowed to return to equilibrium, potential energy is released in the process because the system becomes increasingly stable, right? So, and I just want to go take a second to review free energy, or the change in free energy, or the energy available to do work. So remember that in a reaction, if Gibbs free energy is less than 0, the reaction is spontaneous and reaction goes to completion, where 100% of A converts to B, and the reaction releases energy, and therefore we call this reaction exergonic. If delta G is greater than 0, then the reaction is spontaneous and the reaction doesn't go to completion. Hence, 100% of A remains without any of it being converted to B. For this to occur, for A to be converted to B in this case, we have the reaction will require energy, and hence we call this an endergonic reaction. So this is where we combine the two concepts of both equilibrium and free energy. So to do this, we imagine a simple chemical reaction and interpret it on a spectrum. Let's say 20% of A is present, and 80% of B is 80% of B in this concentration is present. So if we consider the percentages to be relative concentrations of each other, we put them on a scale. We plug them in back to the original equation of the equilibrium constant, where the equilibrium constant is equivalent to the concentration of the products over the concentration of the reactants. We see that 80% over 20% is equivalent to 4, right? So in a general case, the concentration of the products is less than the concentration of the reactants, and therefore the concentration of the products is over the ratio of the products over the concentration of the reactants is less than 1. So we can see here on a scale that the equilibrium constant is favored at 4, right? So we have to show that, yes. Okay, so what happens here is that at KEQ is the natural point on the scale of equilibrium, where because we want the system tends to shift to a KEQ of 4. The concentrations will shift. The relative concentrations of the products and the reactants will shift to establish this ideal ratio of 4. So in this example here, we see here that the equilibrium shift, any concentrations of A that is greater than 20% will shift towards, any relative concentrations of A higher than 20% will cause the equilibrium to shift in the favor of B, where a lot of the concentration some reactant A will be converted to B until the relative concentrations are back at this ideal concentration ratio, 80-20. Right? So yes, so KEQ is a point in a reaction where the forward and backward reaction rates are equal and are characteristic for a specific reaction. So in the general case, the dominant reaction, so as I explained before, so in the dominant reaction, when KEQ is less than 4, a lot of A will be converted to B, and therefore G is less than 0. Therefore energy is released, because this is the natural tendency that we tend to observe here. If the concentration or the KEQ is less than 4, A will be converted into B. If the KEQ is greater than 4, conversely speaking, B will be converted back to A to establish that 20%. So say for example, if the product concentration, if B has a concentration greater than 80%, B will be converted back into A. So there will be a decrease in concentration until it is back at that equilibrium. So Note that these reactions are spontaneous when KEQ is less than 4 and KEQ is greater than 4. And both reactions are trying to reach equilibrium, right? So at any point, the further away the reaction is from equilibrium, the greater the magnitude of delta G and vice versa. So now we're going to look at a case where going against equilibrium and trying to reach 100% of the reactants or 100% of the products leads us. So the further we try to move away from, so essentially what's happening here is that the further we try to move away from equilibrium, the more energy that is needed to reach a specific KEQ. So say, for example, if we go in the direction of A, if we want to convert more product of B into A, away from KEQ equals 4, we're going to have to put a lot more energy into this system. That's what this entire thing is saying. Okay. So going back to the idea of equilibrium, yeah, this is, oh yeah, we haven't covered this yet either. So for a given reaction, A plus B, for A plus B converts to C plus D. Yeah, this is the same thing. This is just essentially what I'm talking about here. The idea of equilibrium and how the system will try to always establish equilibrium based on where KEQ or... Oh, no. What happens here is that, yeah, for Q is just essentially, yeah, Q is just a ratio. It's a, yeah. That's, I didn't specify that earlier. I overlooked this, but essentially the reaction quotient Q, or Q cell or QR is a ratio quantity or quantity that acts as a source of measurement of the relative amounts or concentrations of products and reactants in a mixture at a particular point in time. Q does not have to be equal to KEQ. It can be determined at any particular point of a reaction. So the analogy here is that it can be used as a snapshot of a reaction at a particular point in time, providing info about the relative amounts of products and reactants and the position of a reaction relative to its equilibrium. Thus, in finding this, we can determine the spontaneous direction of a reaction. Q is typically used to represent the relative concentrations of the reactants and products at the steady state of a system. In essence, when the concentrations are constant but system is not equilibrium. Yeah. We also have to consider the standard. Consider the standard conditions proposed in a system. So we gotta be aware of the conditions in biochemical reactions and differentiate between standard conditions in chemistry and transform standard conditions in biochemistry. So the standard conditions in chemistry, right, are where the reactants, and the products are, the concentration of the reactants is equal to the concentration of the products, which is also equal to which is equivalent to 1 molar concentration. So we also find that the pressure is 1 atmosphere with a temperature equal to 298 Kelvin or 25 degrees Celsius. I mean, these two conditions are applied across as well for transform standard conditions as well, but what we really want to look at here is that we want to look at the Q of the cell. Hold on. We want to look at the reactions from a different light in applying the formula for Gibbs free energy, because a lot of the time we're trying to quantify how much free energy is available once a reaction occurs in a system. So yes. Yeah, so as I showed here, that the standard conditions in chemistry are the same as the standard conditions in biochemistry, relatively speaking. The difference is that reactions occur at a pH of 7 for biochemical reactions, right? Biochemical reactions occur in buffered solutions to ensure a pH of 7 or a concentration of hydrogen ion remains constant even if a chemical reaction produces or consumes hydrogen ions. Reactions occur in diluted solution when the concentration of water equals 55.5, or where the concentration of water is equivalent to 55.5 molar concentration at a constantly. If a reaction produces or consumes water, the concentration of water will change minimally, and therefore the concentration of water doesn't need to be included in calculating the equilibrium over the quotient of the cell values. So if we see here, we want to practice how to algebraically solve for KEQ, or a ratio of the equilibrium constant over the quotient. So delta G equals negative for all chemical reactions for Gibbs free energy. Delta G equals negative RT ln KE equilibrium constant over Q. Now for all reactions in standard conditions, delta G equals negative RT ln KQ over Q. And because we can assume that the reaction, or that Q is equal to 1, right? We can just factor out Q and just replace the equation with negative RT ln Q equilibrium constant. Now, for all reactions, before that, at equilibrium, KEQ equals Q equals KEQ, right? And if the ratio between the two is 1, then negative RT ln 1 will get you 0. So delta G essentially equals 0, right? Which means that there is no energy available to do work in the system. So we essentially consider the system to be at equilibrium. Now, for all reactions in biochemical standard conditions, delta G prime standard equals negative RT ln KEQ over Q cell, which is equivalent to negative RT ln KEQ. So similar to for all chemical reactions under standard conditions. Yeah. And I'll just leave this here if anyone wants to know how have an idea of how to calculate, how to do calculations involving KEQ, Q cell, and delta G standard. Okay. And we'll take a break and be right back. Alright, we're back, and now this next half of the session is all about explaining phosphoryl group transfers, or phosphate group transfers between compounds. So we're essentially just going to be explaining phosphoryl group transfers between phosphorylated molecules and ATP. Now, the key idea here is to understand that the free energy change, or Gibbs free energy, is large and negative, meaning that there is a lot of potential large amount of potential energy associated with phosphate group transfers, or for ATP hydrolysis, which is just referring to the cleavage of a phosphate group attached to ATP that forms ADP plus the inorganic phosphate group. So this mechanism exploring ATP hydrolysis explains why the free energy change is so large and negative, or is large and negative. So we can see here that the charge of this molecule, or the charge of ATP, has a charge of -4. We can see here that there is a water molecule acting as a sort of nucleophile that nucleophilically attacks the phosphorus group right here, pushing the electrons to shift towards this oxygen atom right here. While at the same time, there's also another intermolecular reaction occurring where another phosphate group actually nucleophilically attacks, or no, this is incorrect. There's an intermolecular reaction occurring where there's a proton transfer. So there's a proton transfer happening between this for this oxygen here, and this oxygen is acting as a nucleophile from the hydroxyl ion that's formed. So we can see here that hydroxyl ion forms, and what we're going to observe here is essentially the loss of a leaving group, since the electrons from this oxygen atom here pushes the electrons here to form a double bond with the phosphate, allowing it to become chemically stable and thus act as a proper leaving group. So this will readily form the phosphate group, and then what we have here is ADP, or adenosine diphosphate, because there's 2 phosphate groups present now instead of 3. Now, this is a very important part of the reaction here. The reaction here with this phosphate group shows that there are 3 resonance forms shown here, hence demonstrating its chemical stability. So we can see that on this, we can see that on this side of the reaction, or on this side of the equilibrium sign, we can see, literally speaking, that there are several resonance forms. And in organic chemistry, we learned that the greater the number of resonance forms, this doesn't apply to all chemical reactions, obviously, but for the majority of chemical reactions, we find that the more resonance forms there are of a molecule, the greater the greater the stability that molecule tends to exhibit. So we see here that when this inorganic phosphate formed, the charge was delocalized. So we can see here all of these oxygens are spreading the charge apart relatively equally, hence demonstrating greater stability in this for this product. So because the products are relatively more are chemically stable relative to the reactants, this reaction would tend to have a greater this reaction would be considered exergonic, because the Gibbs free energy is large and negative, as shown here. So just to clarify, there's a great amount of potential energy associated with this reaction, this entire reaction, because the inorganic phosphate formed tends to exhibit a great number of resonance, or 3 resonance forms, which is greater than the resonance forms associated with ATP. And ATP is considered to be what we call a high energy intermediate, which we'll cover later. But for now, just understand that this inorganic phosphate is chemically stable, relatively chemically stable. Yeah, so this is just the notes explaining this mechanism. It's everything I've said, but yeah, the newly formed inorganic phosphate is stabilized by a resonance hybrid, right? And charge oh yes, there is one more thing that we actually need to note here. So the charge separation. So if you've noticed here that each of these individual oxygens all have a negative charge, and because the charge are physically placed close to each other, there's a great tendency for these atoms to repel against each other, right? So by by allowing for ATP hydrolysis, the charge essentially physically separates, allowing for the relief of some sort of pressure generated from electrostatic repulsion between the negatively charged oxygens on ATP. Right, that's another contributing factor. So there are two key contributing factors here to ATP hydrolysis, or that favor the exergonic, or there are two factors here that contribute to that favor the reaction of ATP hydrolysis, and hence the exergonic release of energy associated with this reaction. It's charge separation and the formation of an inorganic phosphate, which is stabilized by a resonance hybrid. Okay. Now, other molecules will also tend to have a similar pattern here. So the free energy change is also large and negative for phosphorylated compounds. So this means anything that has an organic that has a phosphate group attached to it. So the cleavage or hydrolysis of the phosphate groups in phosphorylated compounds is exergonic and releases energy, and works similarly to ATP hydrolysis. So there's a couple notable examples. Phosphoenol pyruvate. This is going to be important later when we go through glycolysis in the citric acid cycle. So yeah, I didn't go through these reactions too much, but essentially what happens here is that there is a hydrolysis reaction that occurs here since water is inserted, right, to form pyruvate, and allows for the pushing of a leaving group, which is the inorganic phosphate. What forms is a pyruvate or an enol, or a pyruvate molecule which contains an enol, which is just a vinylic alcohol, right? And this enol and this pyruvate molecule in its enol form will tautomerize, which just means that this enol will be converted into a ketone, right? As shown here. This ketone right here. And the tautomerism just refers to tautomers, which are just essentially two constitutional isomers, right? Now, a similar thing happens. Oh, no, not similar. But with 1,3-bisphosphoglycerate, we can see a similar pattern happening where hydrolysis occurs and the inorganic phosphate is pushed serves as the leaving group, which forms 3-phosphoglyceric acid, right? And what we see here is that once the proton leaves, right, once this proton leaves and forms and becomes a hydrogen ion, we see here that the reaction here is also stabilized by resonance. So this is also a common pattern that we find here, is that resonance tends to occur. Oh, second. Yeah, so 3-phosphoglycerate is resonance stabilized. The last molecule that shares a similar pattern is phosphocreatine. So phosphocreatine is also hydrolyzed to forms the leaving group, which is the inorganic phosphate, and then we get creatine, which is also resonance stabilized, right? It's a bit atypical from the others, because typically what we saw with resonance stabilization is the spread of a negative charge, but this time we see that the negative charge, it's a positive charge that is being delocalized here, where it's spreading between these two amine groups. And lastly, we have thioesters. Now, thioesters are a very special case. Thioesters don't contain inorganic phosphates, but they're similar in the sense that they release a lot of potential free energy when it undergoes hydrolysis. So, in the example of coenzyme A, which is a type of thioester, we see here that there's hydrolysis, and the we see that the thioester undergoes hydrolysis, forming acetic acid, right? And once we find that acetic acid tends to dissociate to form acetate, we see that the acetate is stabilized by resonance. So we see that this reaction is also favorable because of the stability of the products relative to the reactants is greater. So the stability of the products is greater than the stability of the reactants. Hence, this reaction being favorable. So, compared to typical esters, thioesters contain a lot of potential energy, and this is because thioesters aren't. So it's talking about the reactants. So the thioesters aren't resonance stabilized. So if I go here, we see that thioesters are unstable relative to the products because there's poor charge distribution, there's poor orbital overlap, and there are poor resonance structures. I didn't get to write that down. Poor resonance hybrid. Right, so you can see here that the charge, that if there was a resonance form here created, this resonance form is relatively poor compared to this one. Right, like this resonance form creates two charges, and the charge, this is a poor resonance hybrid because not only does this resonance form have two charges, the positive charge resides on sulfur, which is similar in terms of electronegativity, which means the tendency to keep electrons rather than donating electrons to other ions. This charge here is placed on the sulfur ion, which is not typically observed. Hence, we see that that the reactants are unstable, and thus favors less favors its hydrolysis because the reactants are more stable. There's proper charge distribution, meaning that the charge resides on the appropriate atom, in this case the oxygen. There's good resonance structures, and in this particular case, all resonance structures contribute equally to the resonance hybrid, and there's good p orbital overlap between C and O for the pi bonds. Therefore, thioesters readily react to be hydrolyzed, which can facilitate the incorporation of an inorganic phosphate molecule since it releases energy upon hydrolysis. This is just another thing showing that an assembly of informational macromolecules, DNA, RNA, proteins, requires energy. So cleaving these two will release energy needed to synthesize or link the new monomer and polymer together. Right? Okay. Now, we're going to combine the process of ATP hydrolysis and the dephosphorylation of a phosphorylated compound. So we're just combining the two processes I explained earlier to describe how a typical reaction would work. So this is the given reaction. So glutamate is converted into glutamine by some sort of arbitrary enzyme. Obviously, the enzyme, there is a very specific enzyme that is responsible for this whole process occurring. I just can't recall the name at this time. But essentially what happens with glutamate is that glutamate is phosphorylated by ATP, where the ATP undergoes ATP hydrolysis, which forms a glutamate that is phosphorylated. Once that happens, a nucleophile will nucleophilically attack the phosphated glutamate, right? And essentially allow the inorganic phosphate to be pushed out, forming what we call glutamine. So let's go through the actual reaction. This is actually a supposed mechanism that I concocted. This isn't actually confirmed. I'm not entirely sure if this is accurate, so this needs to be verified and checked, but I do believe that this has sound logic in this reaction. So essentially what happens here is that glutamate serves as some sort of nucleophile, which nucleophilically attacks the phosphate group, right? Then once the phosphorylated compound forms, we see here that a tertiary, an amine, oh, not an amine, ammonia attacks, right? Some sort of ammonia attacks, right? And forms the loss of a leaf. Oh, yes. It forms, it forms a temporary chiral center. Yes, this is a temporary chiral center, right? Although this isn't necessarily accurate because these two groups are the same, but essentially what happens here is that we observe here the loss of a leaving group and a proton transfer, which forms us glutamine. This is not correct. This is glutamine. Okay. These are the key details of the reaction that I've described. So step 1, glutamate acts as a nucleophile. It facilitates ATP cleavage into ADP plus inorganic phosphate by attacking the phosphoryl or pyrophosphenol or adenylyl group in ATP. So there's 3 possible points to nucleophilically attack ATP. The alpha one is the close. So if you choose to attack the alpha group, the alpha phosphate is the one closest to the ribose sugar. So it's this one right here. The nucleophilic attack here will transfer an adenyl group as the main substituent, and you'll get a nucleophile attached. You'll get a nucleophile adenylyl group plus a displaced pyrophosphate. If we choose to attack the beta group, we'll get a pyrophosphoryl group. Oh, we should make a key distinction here. There's a difference between pyrophosphoryl and pyrophosphate. So pyrophosphate refers to the 5 oxygen atoms as well as no. Ooh, I made a mistake. There was a 6th oxygen. Yeah, there was a 6th oxygen that connected the 2, right? And I didn't consider. Yeah, I made a mistake here. But yeah, essentially, you guys can essentially see what I mean with the visuals that I've portrayed here. That the pyrophosphoryl group includes the two phosphoryl groups, excluding the oxygen atom here. If it included the oxygen atom here, then this would be considered a pyrophosphate group. Yeah, this may be important to discern because I'm pretty sure that I myself also made the mistake of transferring just the entire pyrophosphate group, when in reality this isn't actually correct. It's just this part that is covalently attached to the nucleophile, not the pyrophosphate, not the extra oxygen atom shown here. And then there's the gamma group, which is the furthest from the ribose sugar. Now this will transfer a phosphoryl group, not a phosphate. Okay. Now, step 2. A nucleophile, a list of which can be shown below, will attack the C-sp2 carbon and cause the pyrophosphoryl or adenylyl group to leave. Now remember that the phosphoryl, pyrophosphoryl, or adenylyl group is a very good leaving group because the product, the inorganic phosphate, is resonance stabilized and largely contributes to the exergonic release of free energy. So, just as I described before, once that inorganic phosphate group forms, right, by doing so, it releases a lot of potential energy, which allows the nucleophile to effectively attack the molecule of interest, which in this case was the formerly, which in this case was the phosphorylated glutamate, right? Or the intermediate compound. Hence, once we see the loss of the leaving group plus a proton transfer, we get glutamine. Okay. So in terms of energetics and reactions, the first two steps shown here in this reaction mechanism are partially correct. What actually occurs are two separate individual reactions that are coupled together to form an overall reaction. So this is I believe this is what we called coupling reactions. So the first reaction was, the hydrolysis of ATP. And then the second reaction was the reaction between some sort of... No. ATP hydrolysis is the first reaction, and then and then the main reaction that we choose to form was the reaction between glutamate, and the ammonium ion to form glutamine and water. And this would be the overall reaction that's shown below here. And then these are just the energetics diagrams. So these are just values that I obtained from my lectures, but I'm pretty sure that this information can be found under standard conditions. These are the actual concentrations that you'll be dealing with. So the concentration of ATP is 5 millimolar concentration. The concentration of ADP is 1.5 millimolar concentration. The concentration of the inorganic phosphate is 10 millimolar concentration. So you obviously want to convert these all into the same unit, which in this case I chose to convert them all into molar concentrations because that's just the standard way of how we really do calculations. You assume that the KEQ equals 2.2 times 10 to the 5, and negative RT equals negative 2478 joules per mole. Right? Now, we also need to consider the fact that a lot of these values are pulled, and I'm pretty sure that the sources were varied, but I'm pretty sure that you'll be able to find these values somewhere. I'll leave this here for everyone else to interpret if they need to, but I think these reactions clearly show how these two reactions are coupled together and how they show that the overall reaction is considered to be a spontaneous reaction. Like if you can see that the basic math, that negative 45 plus 32 kilojoules per mole gets you negative 13 kilojoules per mole. And since that value represents the total amount of energy available for this overall reaction, we consider this overall reaction to be spontaneous. Hence, this reaction will occur naturally. I just wanted to elucidate a little more on the idea of high energy intermediates. So high energy intermediates refer to temporary products. They're not products because they're intermediate compounds where once they undergo hydrolysis, they'll release a certain amount of potential energy, which is greater than the energy released which is either greater than or equal to the energy released by ATP hydrolysis, negative 45 kilojoules per mole under similar conditions. So notable high energy intermediates include acyl phosphates, where R equals H, a CH2 compound, so part of a chain, an oxygen atom that has a charge, or an amine, an amine. Acyl thioesters are high energy intermediates, as we've shown before. Acyl nucleotides, so just refers to acyl nucleotides, so acyl NDP and acyl NMP. So nucleotide sugars are referred to as NDP. NDP is just it's just a generic term that refers to some sort of nitrogenous base plus diphosphate, right? So you can see that there's two phosphate groups and then the nucleoside. sorry, the nucleoside, the nitrogenous base here. So there would be a nitrogenous base here present in this nucleoside for this entire thing. So you'll have either adenosine or uracil diphosphate. Yeah, ribose sugar plus a base. Yeah, the key tip, consider the relative stability of both the products and the reactants and ask yourself, is the formation of the product worth it? Will the product achieve greater stability by undergoing a reaction? That's just the generics of how a reaction should work. Is the formation of the product worth it? Will the product achieve greater stability by undergoing a reaction? So it's saying that there are a bunch of reactants presented to each other. What is needed? If there's energy needed, then ATP hydrolysis would best facilitate this reaction so that this reaction can occur. So in the case of glutamate reacting with the amine group, that reaction was non-spontaneous, and we found that energy needed to be put into the system. So we needed a second reaction to occur, which in this case is actually the first reaction, which is ATP hydrolysis. ATP hydrolysis produces negative 45 kilojoules per mole, while delta G of glutamate reacting with ammonium requires 32 kilojoules per mole, right, to be put into the system. So the energy released from this reaction will be put into the reaction so that this reaction can occur. Okay. And this is just a diagram explaining the same thing of how acyl phosphates are also reacting similarly to thioesters. They have for the same exact reasons. Acyl phosphates will also readily react. Okay. Now, in contrast, these molecules, the following molecules here shown, are considered not to be high energy intermediate, since the potential energy they release when undergoing hydrolysis is less than the energy released from ATP hydrolysis. This includes glucose 6-phosphate or G6P, fructose 6-phosphate or F6P, or glyceraldehyde 3-phosphate or G3P. Yeah, just understand that these molecules are not high energy intermediates, considering that a high energy intermediate has to be a molecule that produces more energy than the energy released from ATP hydrolysis. With all these considered in mind, I'd say that we're essentially good for this section. So next time we'll be covering the reactions of we'll be covering the reactions of glycolysis, or the breakdown of sugar. Or no. Before we can even go through that, we first also need to consider the reactions of we also need to consider the properties of electron carriers, and we need to go over redox reactions, or oxidative and reductive reactions, or oxidation reduction reactions. Anyways, that's all for this one. See you guys in the next one. Thank you.